Hello and welcome. Trigonometry. And inverse trigonometry because it's more fun. This is not quite an enrichment. It's a 4.5 star question in my books and exams. And we're trying to prove that 2 lots of the arctan of 3/2 plus the arctan of 12/5 is in fact equal to pi. How do we approach a problem like this? Okay, as a rule of thumb, when you're looking at inverse trig quantities, think of them as angles. I know they're not angles, but it does help if you do think of them as angles. So what we're going to say here is we're going to say let theta is equal to the arctan of 3/2. And similarly, let phi, a different angle. You're going to use A and B, perhaps probably would have been better. Phi is equal to the arctan of 12/5. So if we need now the tan of theta somewhere in the question, the tan of theta, of course, will be 3/2. And similarly, the tan of phi would be 12/5. And it's worth noting here, because of course this equation now, I'm going to write it above it, actually reads 2 theta, because of course the arctan of 3/2 is theta, has become 2 theta plus phi is equal to whatever. This we cannot put is equal to pi because of course we're trying to prove it, so it's equal to something which we hope is going to turn out to be pi. And let us notice that this the arctan of 3/2 and the arctan of 12/5 is some number between 0 and 90 degrees, or 0 and pi over 2. So the quantity 2 theta plus phi is bounded. In other words, it cannot be outside this interval. It has to be definitely positive, okay? And since the arctans that we have in there, they can be at most 90 degrees, up to pi over 2, basically. We got 2 lots of pi over 2 plus another pi over 2. It should be as much as 3 pi over 2. We're going to need that, I'm sure, at some point in the question. If we don't, it's just worth kind of like being aware of what's happening around us. Okay, so where do we go with this particular question now? We've done the preliminaries. We need to make a start. So we're going to write, of course, 2 theta plus phi is not equal to pi, of course. Oops, I wrote theta again. 2 theta plus phi is equal to some other angle. So we call it perhaps psi, my favorite Greek letter, a trident. Because, of course, I have tans in the question, I'm going to tan this equation. Let me write it back to front as well. So the tan of psi is equal to the tan of 2 theta plus phi. Then I'm going to use my compound angle identity for tan A plus B. So the tan of psi on the next line is equal to the tan of 2 theta plus the tan of phi, the whole thing over 1 minus tan 2 theta tan phi. I can see where this is going. For example, now on this line here, I can actually put in there tan phi is 12/5, so that can go in 12/5 and 12/5. But unfortunately, I don't know what the tan of 2 theta is. I know what the tan of theta is. So it's going to get a little bit messy, and probably I might just do it equal here. Let's make a big fraction line, and I hope you know all your trig identities. The tan compound, the tan double angle, we don't often remember them well because we don't use them as often, but in this question we do need them. So I'm doing now the tan of 2 theta here, so that's going to be 2 lots of the tan of theta over 1 minus tan squared theta, that is that, plus of course the tan of phi, and at the bottom I go 1 minus the tan of 2 theta, which is that, 2 tan theta over 1 minus tan squared theta, but this time is times the tan of phi. And perhaps I'll do equal, 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 so that's still equal to the tan of psi, because now all these numbers are here. So let's start putting them in. 2 lots of the tan of theta. The tan of theta is 1.5, so that's going to be a 3. So that's the main fraction, that's a 3 there. 1 minus tan squared of theta. That's 9/4. Squaring 3 over 2 is going to give me 9/4. So that is that, plus the tan of phi, which is 12 over 5. You could, of course, use your calculator. I can't be asked. So that's going to be 1 minus, this quantity here is exactly as that, which is exactly as that. 3 over 1 minus 9 over 4 times 12 over 5. Just a little bit of tedious tidying up now on this particular one. I'm just looking at this fraction here. It's a triple double fraction. I don't know what you call this. We got a fraction line, we've got another fraction line, we've got more fractions within the denominator of this double fraction. So I'm looking at this lump here. I'm going to multiply top and bottom of this lump by 4 first of all. So that's going to give me 12 on the top, and at the bottom times by 4, it becomes a 4. Take away 9, so that's this bit here. I'm not doing anything else to the rest. I'm doing it step by step, because even to type this into a calculator would just stress me out. I can't be asked. So 1 minus, this is exactly the same as that. 12 over, let's put now this a minus 5 there. I can see it from there. Times at 12 over 5. And of course, let's return to the left because I ran out of space. The tan of psi, what is it equal to? This is going to be equal to 12 over negative, let me just make some more room, it'll be crammed in there. So it is 12 over negative 5. 12 over negative 5. Well, plus 12 over 5, and on the bottom we're going to have 1, that's a plus 144 over 25, which of course is now equal to 0. It doesn't really matter what that is non-zero, some number, but 0 divided by anything is in fact 0. So the tan of psi is equal to 0. What does that actually mean? Well, it means that your psi, thinking about the tan graph or the tan solutions, the equation tan psi is equal to 0, will be dot dot dot, let's say minus 2 pi, minus pi, 0, pi, 2 pi, 3 pi. It repeats every 180. Okay, so how do we know now? Because of course we said this particular quantity is psi, so these two things added together is one of these numbers in here. And remember, I bounded a quantity between 0 and 1.5 pi, so we can't be 0, have to be strictly positive, and the only number that's in that range is just this pi here. Okay, therefore psi is equal to, of course, pi. And just to be nice with the question, I do not like leaving things halfway, therefore I'm going to write it here because I have no space. Therefore the 2 lots of the arctan of 3 over 2 plus, let's move the other way, the arctan of 12 over 5 is equal to pi as required. So that concludes the proof, and this was done by using ordinary trigonometry. It's perhaps a little bit involved the first time you see it. I used to hate as a learner inverse trig bits and this kind of setups, but they're quite enjoyable once you crack them, and it's quite enjoyable once you begin to see what's going on and start manipulating them. Worth a go. Okay. When I was doing this question, it wasn't actually planned. So I'm going to make the lecture a little bit longer, and I did say this was standard maths, but now I'm going to go into further maths. I want to do something with this question which does involve very basic further maths, and in particular elementary complex numbers. So I'm going to come up with the same answer, but in a completely different way. So if you're a standard mathematician, please ignore this part of the lecture. But if you understand a little bit of complex numbers and some of the basic properties, please hang on, because I'm going to show you a very beautiful way of actually proving this result. And the way it goes a little bit like this. I'm going to put up here a little picture. This is the Argand diagram, or the complex plane, if you prefer this word. This is the real Z, and this is your im z. And for numbers which lie on the positive x and positive y. It doesn't have to be, but I'm just doing it there because of the numbers that I'm going to use. Something with sub there, let's say a z with sub there, then the argument of z is equal to, the arc, let me just make a little bit more room because it's not going to fit. The argument function, the argument of z, if you're there, is going to be the arctan of imaginary z over real z. The same is true if you're on the fourth quadrant. If you're here, is that plus pi, and if you're there, is that minus pi. But the numbers that we're going to use are in the first quadrant. So keeping that in mind now, I'm going to start with something that perhaps we just need to see where I'm going and what I'm doing. See this bit here, it looks a little bit like an arctan of imaginary over real. So I'm going to say the following. I'm going to consider the following expression, or number expression. I don't know if you can still call it expression, it's just numbers. This is the I bit and it's the real bit. So 2 plus 3i, and this 2 at the front, I'm going to put it squared like this, and I'm going to multiply it by the arctan of 12 over 5, so I need 5 plus 12i. That's my real and that's my imaginary. So that's going to be 5 plus 12i. And I'm going to multiply it out just to see what I get for something like this. So ordinary complex numbers, square in the bracket, 4, multiply together and double, you're going to get 12i. This bit squared is going to be a negative 9, and still to be multiplied by 5 plus 12i. And we continue from there. This is equal to negative 5 plus 12. Let me just write this first because it's easier. 5 plus 12i, and this will now give me a negative 5 plus 12i. Negative 5 plus 12i. And I'm going to do another swap. Sorry about that. My brain is needs to see it a little bit differently. So 12i plus 5, 12i minus 5. Perhaps you can guess what I'm trying to see without doing any multiplications. That's the difference of squares. So it's going to be 12i all squared, which is negative 144, and minus 25, which of course is negative 169. Okay. So far so good, nothing complicated. So I'm going to write that is equal to negative 169 and rub off the rest. I don't care about the rest. This is now what I have got so far. Okay, what's my plan next? Of course, you know, when I was looking at the argument function that has arctans and I was trying to make these quantities to fit my problem, I'm going to arg both sides of this equation. So the argument, I'm going to put square bracket so we can all follow exactly what I'm doing step by step. I'm going to put detailed workings on this. Is equal to the arg of negative 169. Okay, property of the argument function. The argument function behaves very much like a log, and I'm not going to get into why it does that. So it's the same way if you had the log of a times b, you can split it into two separate logs. So it's all part of your course, I believe. It's not something that is unusual or something that you might be seeing in this lecture for the first time. So that's that plus the argument of 5 plus 12i. And shall I evaluate, because this of course I know what the argument of negative 169 is. Where's the 169 negative? Is here, somewhere here, minus 169. What's the argument when you're on the negative x-axis? The answer is pi, or 180 if we're working in degrees. So far so good. We've got this quantity. What's our next step? This square here, I can move to the front. If you don't like it, it's like again, as I said, like a log. If you write this quantity as two brackets, 2 plus 3i times the 2 plus 3i, again, you can split it into two separate arguments, and then of course it's going to be exactly the same quantity. You can put it together. So I hope you're following what you can do instead. This you might not have seen perhaps in the standard manipulations, but is actually valid. So 2 coming to the front plus the argument of 5 plus 12i is definitely equal to pi. And now we're looking at where these numbers are. This number, 2 plus 3i, of course, in the first quadrant, and so is this one, 5 plus 12i in the first quadrant. And therefore, by definition of the argument in the first quadrant, this says, in fact, the arctan, so 2 lots of the arctan of what? The imaginary part over the real part. 3 over 2, that's this bit here, plus the arctan again, imaginary over real, so the imaginary is 12, the real is 5, should be equal to pi. Is that what we're trying to prove? It is. Who's laughing now?